Hello everyone. I'm Ricardo from Igalia, and I'm going to talk about device-generated commands in Vulkan. So first, some bits about me. I have been part of the graphics team at Igalia since 2018. For those that don't know us, Igalia is a small consultancy company specialized in open source. And my colleagues in the graphics team work on things such as MISA drivers, Linux kernel drivers, compositors, that kind of thing. In my particular case, the focus of my work is contributing to the Vulkan conformance test suite, and I do that as part of a collaboration between Igalia and Valve that has been going on for a number of years now. Just to highlight a couple of things, I am the main author of the tests for the mesh shading extension and device-generated commands that we are talking about today. So what are device-generated commands? So basically, it's a new extension, new functionality that allows a driver to read command sequences from a regular buffer, something like, for example, a storage buffer, instead of the usual regular command buffer that you use. The contents of the DEC buffer could be filled from the GPU itself. So this is what saves you the round trip to the CPU, and that way you can improve the GPU-driven rendering process in your application. It's like one step ahead of indirect draws and dispatches and one step behind word graphs, essentially. And it's also interesting because device-generated commands provide a better foundation. If you have a translation layer that implements the X12 on top of Vulkan, like, for example, Proton, and you want to implement execute and direct, you can do that much more easily with device-generated commands. This is important, like I said, for Proton, which Valve uses to run games on the Steam Deck, Windows games on top of Linux on the Steam Deck, for example. So if we set aside Vulkan for a moment, we start thinking about GPUs and stuff, and you want to come up with a naive CPU-based way of running commands from a storage buffer. How do you do that? Well, one immediate solution we can think of is, well, first of all, I'm going to assign a token, an identifier to each of the commands I want to run, and I'm going to store that token in the buffer first. And then depending on what the command is, I want to store more information. So for example, if we have a sequence like we see here in the slides where we have a push constant command followed by a dispatch, so I'm going to store the token for the push constant command first, then I'm going to store some information that I need for the push constant command, like the pipeline layout, the stage flags, the offset, and the size. And then after that, and depending on the size that I said I need, I am going to store the data for the command, which is the push constant values themselves. And then after that, I'm done with it, and I store the token for the dispatch, and then the dispatch size, and that's it. But this doesn't really work. This is not how GPUs work. A GPU would have a hard time running commands from a buffer if we store them this way. And this is not how Vulkan works, because in Vulkan, you want to provide as much information as possible in advance, and you want to make things run in parallel as much as possible and take advantage of that. So what do we do in Vulkan? So in Vulkan and in the VKEXT device-generated commands extension, we have this central concept, which is called the indirect commands layout. So this is the main thing. And if you want to remember just one thing about device-generated commands, you can remember this one. This is the main thing. So the indirect commands layout is basically like a template for a short sequence of commands. The way you build this template is using the tokens and the command information that we saw colored red and green in the previous slide. And you build that in advance, and you pass that in advance, so that in the end, in the command buffer itself, in the buffer that you are filling with commands, you don't need to store that information. You just store the data for each command. That's how you make it work. And the result of this is that the commands layout is this template that I said is a template for a short sequence of commands. And by short, I mean a handful of them, just 3, 4, 5 commands, maybe 10, I don't know. So that in the end, the DEC buffer can be pretty large, but it does not contain a random sequence of commands where you don't know what comes next. It contains, you can think about it as divided into small chunks that the specification calls sequences. And you got a large number of sequences stored in the buffer, but all of them follow this template, this commands layout. So in the example, we had push constants followed by dispatch. So the contents of the buffer would be push constant values, dispatch size, push content values, dispatch size, many times repeated. The second thing that Vulkan does to be able to make this work is that we limit a lot what you can do with device-generated commands. There are a lot of things you cannot do. In fact, the only things you can do are the ones that are present in this slide. So you got some things like you can, for example, update push constants. You can bind index buffers, vertex buffers, and you can draw in different ways using mesh shading maybe. You can dispatch compute work, and you can dispatch a retracing work, and that's it. You also need to check which features the driver supports, because maybe the driver only supports device-generated commands for compute or ray tracing or graphics or something like that. But you notice you cannot do things like start render passes or insert barriers or bind descriptor sets or that kind of thing. No, you cannot do that. You can only do these things. So this indirect commands layout, which is the backbone of the extension, specifies, as I said, the layout for each sequence in the buffer. And it has additional restrictions. The first one is that it must specify exactly one token that dispatches some kind of work, and it must be the last token in the sequence. So you cannot have a sequence that dispatches graphics work twice, or that dispatches compute work twice, or that dispatches compute first and then draws, or something like that. No, you can only do one thing with each DGC buffer and each commands layout, and it has to be the last one in the sequence. And one interesting thing that also Vulkan allows you to do, that DX12 doesn't let you do, is that it allows you to switch on some drivers. You need to check the properties for this. On some drivers, it allows you to choose which shaders you want to use for each sequence. So this is a restricted version of the bind pipeline command in Vulkan. You cannot choose arbitrary pipelines, and you cannot change arbitrary state, but you can switch shaders. So for example, if you want to use a different fragment shader for each of the draws in the sequence, you can do that. This is pretty powerful. How do you create one of those indirect commands layout? Well, with one of those typical Vulkan calls to create an object that you pass these create info structures that are always present in Vulkan. And as you can see, you have to pass the shader stages that will be active while you draw, while you execute those indirect commands. You have to pass the pipeline layout, and you have to pass an indirect stride. The stride is the amount of bytes for each sequence, from the start of a sequence to the next one. And the most important information, of course, is a list of tokens, an array of tokens that you pass as the token count and then the pointer to the first element. Now, each of those tokens contains a bit of information. The most important one is the type, of course, and then you can also pass an offset. And together with the stride, this offset tells you how many bytes into the sequence for the start of the data for that command. It tells us that you don't need to pack the data for those commands together. If you want to include some padding because it's convenient or something, you can do that. And then there's also the token data, which allows you to pass the information that I was painting in green in other slides, like information to be able to run the command with some extra parameters. Only a few tokens, a few commands need that. You need to, depending on the command that it is, you have to fill one of the pointers in the union. But for most commands, they don't need this kind of information. Knowing which command it is, you just know you are going to find some fixed data in the buffer, and you just read that and you just process that. One thing that is interesting, like I said, is the ability to switch shaders and to choose which shaders are going to be used for each of those individual sequences. So some form of pipeline switching, restricted pipeline switching. And to do that, you have to create something that is called indirect execution sets. So each of these execution sets is like a group or an array, if you want to think about it like that, of pipelines, similar pipelines or shader objects that have to share something in common, which is that all the state in the pipeline has to be identical, basically. So only the shaders can change. And when you create these execution sets and you start adding pipelines or shaders to them, you assign an index to each pipeline in the set. And then you pass this execution set beforehand, before executing the command, so that the driver knows which set of pipelines you are going to use. And then in the DGC buffer, when you have this pipeline token, you only have to store the index of the pipeline that you want to use. So you create the execution set with 20 pipelines, and you pass an index for the pipeline that you want to use for each draw, or for each dispatch or whatever. So the way to create the execution sets is the one you see here, where we have, again, one of those create infrastructures. We have, then there we have to indicate the type, which is pipelines or shader objects. Depending on that, you have to fill one of the pointers from the union on the top right here. And then, for example, if we focus on pipelines, because it's easier, on the bottom left, you have to pass the maximum pipeline count that you're going to store in the set, and an initial pipeline. The initial pipeline is what is going to set like the template that all pipelines in the set are going to conform to. So they all have to share essentially the same state as the initial pipeline. And then you can change the shaders. With shader objects, it's basically the same. You have to pass more information, of course, for the shader objects, like the descriptor set layouts used by each stage, push content information, but it's essentially the same. So once you have that execution set created, you can use those two functions to update, to add pipelines to that execution set. You need to take into account that you have to pass a couple of special creation flags to the pipelines and to the shader objects to tell the driver that you may use those inside an execution set, because the driver may need to do some things special for them. And one additional restriction that we have is that if you use an execution set token in your sequences, it must appear only once, and it must be the first one in the sequence. And that's an additional restriction. Okay, so the recap so far is that the DGC buffer is divided into small chunks that we call sequences. Each sequence follows a template that we call the indirect commands layout. Each sequence only must dispatch work exactly once, and you may be able to switch the set of shaders we used with each sequence with an indirect execution set. All right, so you have all those elements so far. So how do we go about, actually telling Vulkan to execute the contents of a specific buffer? Well, before executing the contents of the DGC buffer, the application needs to have bound all the needed state to run those commands. That includes descriptor sets, initial push constant values, initial shader state, initial pipeline state. And even if you are going to use an execution set to switch shaders later, you have to specify some kind of initial shader state. And once you have that, you can call this command execute generated commands. So you bind all that state into your regular command buffer, and then you record this command to tell it, yeah. And then at this point, execute the contents of this buffer. So as you can see, you typically receive you pass the regular command buffer as the first argument. Then there's something, a Boolean value there called is preprocessed, which is kind of confusing because this is the first time it appears and you don't know what it is about. We will talk about it in a minute. And then you pass a relatively large structure containing information about what to execute. So in that generated commands info structure, you need to pass, again, the shader stages that will be used. You have to pass the handle for the execution set if you are going to use one. If you're not, you can pass the null handle. Of course, the indirect commands layout, which is the central piece here. And then you pass the information about the buffer that you want to execute, which is the indirect address and the indirect address size to pass the buffer size. So we were using buffer device address to pass information. And then we have something, again, mentioning some kind of preprocessing thing, which is really weird. Preprocess address and preprocess size looks like a buffer of some kind. We will talk about that later. And then you can pass, you have to pass the maximum number of sequences that you are going to execute. Optionally, you can also pass the address of a buffer address for a actual counter of sequences. And the last thing that you need is the max row count, but you can forget about that if you are not dispatching work using draw with count tokens. And it only applies there. If not, you leave it 0 and it should work. So we have a couple of things here that we haven't talked about yet, which is the preprocessing thing. What is this preprocessing thing? Well, starting from the bottom, that preprocess address and size give us a hint that there may be a preprocessing step going on, some kind of thing that the driver may need to do before actually executing the commands. And we need to pass information about the buffer there. And the Boolean value that we pass to the command, execute generic commands, tells us that that preprocessing step may have happened before. So it may be possible to explicitly do that preprocessing instead of letting the driver do that at execution time. So we're going to take a look at that a bit in more detail. First of all, what is the preprocess buffer? Well, the preprocess buffer is just an auxiliary space scratch buffer because the driver is, some drivers need to take a look at how the command sequence looks like before actually starting to execute things. So they need to go over the sequence first, and they need to write a few things down just to be able to properly do the job later to execute those commands. So once you have the commands layout and you have the maximum number of sequences that you are going to execute, you can call these get generated commands memory requirements, and the driver is going to tell you how much space it needs. So then you can create a buffer, you can allocate space for that. You need to pass a new buffer usage flag, which is the one you can see here. And you pass, once you have that buffer, you pass the address and you pass the size in the previous structure, and that's it. Now, the second thing that we have is the possibility, as I said, to do this preprocessing step explicitly. I don't want to go into too much detail, or else I have the risk of running out of time. So basically, explicit preprocessing is something that it's optional, but you probably want to do that if you care about performance. It's the key to performance with some drivers. Now, when you use explicit preprocessing, you don't want to record the state, then call these preprocess generated commands, and then call execute those generated commands, because that is what implicit preprocessing does. So this doesn't give you anything if you do it this way. So this is designed so that if you want to do explicit preprocessing, you probably want to use a separate command buffer for preprocessing, and you want to batch preprocessing calls together and submit them all together to keep the GPU busy and to give you the performance that you want. So you submit the preprocessing steps all together first, while you still prepare the rest of the command buffers and you enqueue the next batch of work. That's the key to use preprocessing optimally. When you do that, you need to decide beforehand if you are going to use explicit preprocessing or not, because if you're going to use explicit preprocessing, you need to pass a flag when you create the commands layout, and then you have to call the preprocess generated commands function. And if you don't pass that flag, you cannot call the preprocessing function. So it's an all or nothing. You have to decide, and you do what you want. One thing that is important to note is that Preprocessing needs to know and needs to have the same state, the same contents of the input buffers as when you execute, so it can run properly. And that poses like a small risk, which is, okay, so if you want me to use explicit preprocessing, I need to use a separate command buffer, but I need to know the state of the things, and I need to know the contents of the buffer that I'm going to use later. So, and they need to be the same ones that we use when we execute. So what do? We have to, all right. So, okay, I was saying that if the preprocessing step needs to have the same state as the execution, you need to have bound the same pipeline state, the same shaders, the same descriptor sets, the same contents. And I said that explicit preprocessing is normally used using a separate command buffer that you submit before the actual execution. You have a small problem to solve, which is that you would need to record a state twice, once on the preprocess command buffer, so that the preprocess step knows everything, and once on the execution, the regular command buffer, what you call execute. So that would be annoying. So instead of that, the preprocess generated commands thing takes an argument that is an state command buffer, and the specification tells you, well, this is a command buffer that needs to be in the recording state, and the preprocess step is going to read a state from it. And this is the first time that, and I think the only time in the specification that something like this is done. So you may be puzzled about what this exactly, how do you use this? How would it pass this? And I just wanted to get this slide out to tell you, well, if you're going to use explicit preprocessing, the ergonomic way of using and how we thought about using the preprocessing step is like this. You take your main command buffer and you record all the state first. And just before calling execute generated commands, the regular command buffer contains all the state that you want and the preprocess needs. So you stop there for a moment. And then you prepare your separate preprocessing command buffer, passing the main one as an argument to the preprocess goal. And then you continue recording commands in your regular command buffer. That's the ergonomic way of using it. So synchronization, yes, you do need some synchronization at some steps. The main one is that if you generate the contents of the DGC buffer from the UPU itself, you're going to need some synchronization. Writes to that buffer need to be synchronized with something else that comes later, which is executing or reading those commands from the buffer. Depending on if you use explicit preprocessing, you can use the pipeline stage command preprocess, which is new, and preprocess read, or you synchronize that with your regular device generated commands execution, which was considered part of the regular draw indirect stage using the indirect command read access. And then, of course, if you use explicit preprocessing, you need to make sure that writes to the preprocess buffer happen before you start reading from that. So you use this stage here to synchronize preprocessing with execution if you use explicit preprocessing. So the quick how-to, I just wanted to get this slide out for those, if you want to reference later, saying exactly what you need to do, all the steps that I mentioned here about, generating the commands layout, the execution set, allocating the preprocess buffer, etc. This is the basic how-to, and that's it. Thanks for watching. Questions?
Could you give an example of when is it beneficial to use device-generated commands, of like a workflow or something like this?
Well, I don't have many real-world experience with full applications and game engines, so I cannot speak about that. But it is true that, for example, some recent games and were released not long ago, like Starfield and things like that, started to use the more advanced things from Execute and Direct in DX12 that allows similar capabilities to try to improve the performance of the games. And this is the same use case. So sometimes doing GPU-driven rendering, and you have a lot of geometry to process that you can you can process that with a compute dispatch, for example, and you can fill a buffer with what you want to draw later, and you save the round trip, and you save, a lot of CPU time because you don't need to specify draw this, draw that, whatever. You don't need to record those commands because you can store them in the DGC buffer directly. It will save you a lot of CPU, so it can be interesting those scenarios.
I've got another question over here.
Thank you. Hi, my question is basically, this extension relies heavily on buffer device addresses, possibly other kind of resources that in a scenario where you want to capture this on one device and replay on another device, a bit like the demo I'm showing outside. Do you expect any specific problems that, like, I don't know, where just handles or addresses could not be used on during replay? So do you see any difficulties with this extension?
Maybe that's one thing for perhaps the GFX reconstruct people to answer. But yeah, the device addresses are used for only for the contents of the buffer, and we have an extension that allows you to capture device addresses to be able to replay them later. So you could use those extensions to be able to capture and replay or to save to disk, and it shouldn't pose a problem as far as I understand. It doesn't use that device addresses that heavily.
I can actually answer one thing about that, about device buffer addresses. Well, RenderDoc has this tendency to turn off, to refuse to capture stuff if you try and use an extension that it doesn't support, with the notable extension being, notable exception being ray tracing. But it does support buffer device address. You can actually get a uint value and cast it to a pointer, and you can actually look at the contents of the buffer as it was like the same address that you had while you were capturing. So that works really well. And I have a question. I don't quite, well, it's probably just because it's so fresh, but what's the deal with the last token being the actual like action thing? And will that prevent me from, for example, using this? Because the one example I can see for using this is, for example, if I cannot afford order-independent transparency, or order-independent transparency is just not feasible, and I have two transparent fragment shaders, and I wish to like actually literally sort my triangles by their depth from the camera, and I want to switch the shaders really fast. And within this whole framework of, keeping the state the same, the pipelines, and only being able to switch the shaders, would that allow me to do that, this extension?
Yes, I think so, because the thing about the dispatch command being the last one, it must be the last one in the sequence. Like you can have a lot of sequences, and each of those has a draw or dispatch at the end of the sequence. So the thing about being the last one is for a single specific sequence, so that the idea is that you change push constant values, or you bind different vertex buffer or index buffers to prepare things for the dispatch or for the draw that comes at the end of each sequence. But then you have a bunch of sequences, and when you dispatch one, unless you pass, if I am not mistaken, unless you pass one specific flag, those dispatches are supposed to happen in the same order as if you have recorded those commands in a regular command buffer. So the draws are ordered and happen in the order that you expect normally. So the restriction is just that when you dispatch work from a single sequence, dispatch thing is at the end, so that you cannot alter state that would potentially affect subsequent sequences. So you have to set a state first or change a state first, and then dispatch some kind of work in each individual sequence. I think that explains it. It's like regular drawing, but you're reading the draw sequence from a buffer, but it respects the order normally.
I think that might have to be the last question, otherwise we're going to start moving on. So if you want to meet up during the break, if that's okay. Thanks very much. Thanks, our speaker.